Okay, my outstanding friends, as I'm sure you have heard of Albert Einstein and his theories about light and particle wave duality. And they do an experiment to show that it has both of these effects. It looks like a wave, but it has to be a particle. But they can't figure it out. Nobody has ever been able to figure out until I got help from Rod Warren, because he did the actual research and shows that it is a particle and it forms a wave. That's it right there. Done. Case closed. Now don't forget, this is not CGI. This is taking raw data, which is nothing more than numbers, and assigning them to energy levels. The higher the number, the more bright the energy is. And because of the way CMOS works, it's all based on CMOS. You can do this, and you can do it in layering, and that's what he's doing, stacked layering. I mean, it's so stunning, it's unbelievable. And it's based on basically my dipole electron flood theory, but he's doing work that nobody else, I could never do this, let me just put it that way. So I'm just glad I was able to get him to respond to me so I can respond back to him. And we talked a couple of times. And he sent me dozens and dozens of shots that are just staggering to the mind. That's all I can tell you. All right. This is from my friend Mason, which I'm showing her all these pictures, the Zeeman effect and all the magnetic fields and so forth. This is academia.edu. You go up there, CMOS sensor data, yada, yada, yada. Now, this is the stuff. I'm going to knock your socks right off. If they don't come off, you better change your socks because they're going to cut off your blood flow. Okay, my friends, this is a rush. This is the sun. It's a dipole. Now, I have a little trouble trying to figure this out yet. So you got your muon side, you got your electron side, the black and the white. But the sun is this size of a disk. And my friend Mason put this up using CMOS sensor data. Data is the numbers assigned to the pixels. And they get that number and it says, that's so much energy. And that's so much frequency, which is here. Frequency determines energy, basically. And it's a dipole. Now, the sun is here. That's the sun. How could that be? I looked at this and yikes. I know it's right because I know the guy who knows what he's doing. I can tell you he knows a lot. Wait till you see the paper. Now, here's a couple of situations that I threw in here. You got your radiation of what I call atomic vapor. And all it is particles of light and photons and some bigger pieces too, yes. But it's coming down. Now, he's down here at the Earth looking out through the surrounding layer of atmosphere. And there's a lot of particles there. I'm not sure how that affects what he's seeing. But it might account for this. I don't know. All I can tell you is this is a mystery to me right now. It's just a mystery. There's a lot of mysteries. So the light is coming through here. And it's banging and banging and it finally hits the Earth where his telescope is. And he sees it. And he takes all of these images that are coming down, because every one of these is layered on top of the next one. So we know almost all the light is, well, basically all the light is coming from that spot, and all the dark is coming from that spot, and it radiates outward according to its energy. Now, so this is about using CMOS and the Zeeman effect to look at dynamic electromagnetic field imaging. Listen to this. This was just a few days ago, or a couple of weeks ago. The image shown above is not computer-generated image or an artist rendition based, but it's based on data. And all it is if you took a whole big block of squares like this, thousands, millions, And they go into the megapixel. They're just absolutely tiny little things. And it's hit with a little tiny frequency here, and another little tiny one here, and another one tiny here. And then it builds an image around that data. Now it knows different frequencies are different colors. You get down into the radio waves and up past into the way out on the other end, there's no color left. You don't see colors. You see energy. That's what you're seeing here is energy. Now, so listen to this. It's primarily based on dipole electron flood theory, which is me. And a bunch of other people. Dylan Carpenter, he mentions, right, he didn't talk about Rod Warren, but Rod was the instigator for the whole thing. I lost track of him years ago. And anyway, I hope he contacts me, because he should be the one that gets credit for this. Anyway, dipole electron flood theory. I'm getting to where I think I can cover most of the thing. But this goes deep. It says current methods of magnetic field detection, collection, and imaging are all using all these different things that they change what you're seeing. They change the data that's coming in. They sort of organize it so they say, oh, I don't want to see all that. I'm serious. It said the methods often require specific environment, Upon investigating methods to reduce camera noise and light and flares, this is what they do. They reduce. They call it noise. It's not noise. It's particles that are giving off signals, but there are so many of them that it looks like noise. It's not noise. And he talks about the Hubble and the Webb and all of that stuff. Now, here's what he used. Tripod, 5-inch Newtonian reflector telescope, 2 times Barlow lens. It goes on pretty serious. And here's the key, is the CMOS. Up to 200 megapixels and down to 0.6 microns sensitivity. Now, he took out all the filters. He was able to disassemble all the things that they put in to obscure what you're seeing. I'm not kidding you. That's just a fact. He's removal of any built-in filters. He cut them all out. He switched to CMOS detection. He did all kinds of things. And it goes on and on here about all kinds of stuff, which I don't understand. Stretching the threshold of detection, reach wavelength of light, This method allows for exploration within new frontiers of amateur. This is not amateur. This is way past that, Mason. I have seen nothing that even comes close to comparing what he did. He's using, just like Rod and I use, a regular cell phone CMOS sensor is capable of producing usable radio telescopetry data in combination with images simultaneously. It'll eliminate the need for 3D rendering. The guy really knows his stuff, my friends. And these are, so look at this. This is Saturn. This is Saturn image 2. Now, he had to take it from a different time of the night or something. I don't know. These are the kind of things I want to talk to him about. I don't know. And again, he's layering these. So this may be a layer that's one shot was way up here, because he's only giving you one shot when he gives you that shot. You're not getting all the depth of layering. At this point, it's one layer. Just like here, it's going to be one layer. How they blend together, I don't know. But they're both Saturn. And this is the sun. And this is Vega, which I believe is a constellation, but he can do, I mean, he knows what he's doing. And this is our moon. And all these little things they call noise. Can you even see that? All those little dots, they take them out. If you see something like that, nobody wants to see that. Well, yes, somebody does want to see it, and now we can see it. This is the Crab pulsar. This is our moon right here. Now check this one out. Look at this. This is the local group of stars. All dipoles. Everything's dipoles. And this one's very interesting. I'd like to see, I'm sure the black one is down here. And this is like a molecule. I mean, I don't know what to say. The interference fringes are clearly visible. He's using raw CMOS data. Now he wants peer review. He wants somebody to look at it. Take a look at it. He credits Dillon for showing these pictures. He sent them to me. He said, "What do you think? I just got a new cell phone." I said, "Yikes. I can't get to hold of him. He can't either." So he's been working with me. Called me a gentleman. And it's about dipole electron flood theory. And I have people proving it all day long, every day. And it's just no getting away from now. So until somebody started to take the time to look at this stuff up, they're just walking around in circles. If you could prove me wrong or show that the things I'm saying are not right, well, let's do it. Let's dance. All right, let's just establish a few ground rules. Particle wave duality. Yes, absolutely. There's the particle. It's moving forward, concussing with all the other fields that are in front of it, making them glow. Anytime the white pushes against other particles that have fields, and every particle has a field, it glows. And that's what we're showing here in Rod Warren's experiments. This right here is that particle. It's coming through the air, it's just coming out of a venturi, which makes it accelerate exceptionally fast. And all of these little white dots in front are the particles in space, the different gases and so forth, oxygen, nitrogen, all that stuff. And they're glowing because the field is pushing against it. That's all, simple as that. And that's the particle is right in there, and as it moves forward, it creates this field. Particle wave duality. There's no mystery here whatsoever. And I've known about this for 50 years or more. And I'm blocked from speaking about it. I mean, literally blocked. All right, if you talk to any physicist, they say the light particles just go like this, up and down. No, they don't. They spin in a circle. If you looked at it sideways, it looks like that, yes. But it's actually spinning like this. The particle is at the end of the spin. And as it spins, it gets pushed against other particles and it keeps it turning in a circle. And that is, and I can prove this, I make no statements whatsoever that I cannot prove. There is what happens with light. As you shine that light down there, once it goes through the venturi, it's split it up. And it's spinning this way. Well, it's quite obvious. I mean, if you can't see that, I don't know, you got issues. It's spinning. The main impact site is the center. These are on the outside because there's a ton of different particles coming down. There's not just one. That is what light does. It spins. It doesn't flap like a wave. It spins, and then you see the wave and you see the particle. And when I say you can see the particle, there is no question. Here's the wave. There's the wave. And it hasn't quite hit the venturi yet. The venturi's down here somewhere. A venturi is just nothing more than a restriction. All that stuff has to force its way through that restriction. When it does, all the fields crush together. And that's exactly what they do at CERN. And I went to University of Geneva for particle physics, and I told them, I said, we're using CMOS, complementary metal oxide silicate semiconductors, to see these particles. And oh, no. Same thing happened to me at Fermilab, yeah, all of them. And I proved it. And then they shut down to incorporate CMOS. Okay, my friends, my intention is to shock the hell out of you. Where do you see what I have to show you about what's in space? So how will I shock you? This is from a friend of mine who has a Newtonian telescope, and he's taken pictures of all the different planets, the constellations, the sun, the moon. This happens to be Saturn. You see this? That's Saturn. Now, here's what you have to look at: the different colors, and this is what it is. This is not him manipulating anything. Blue is a faster light, and the yellow is down in this direction. So this is moving faster, or the light is in the blue range. That's all I can say for now. I don't want to make any statements that I can't really support, because I can't yet. I just had a conversation with my friend Fran, and we went through everything. And after I got off, I said, "Wow, I got to really look at this." And here is the energy. That's the white part, which is the electron neutrino in atoms. And this is the muon neutrino in atoms, the dark part. Look at this. These are like dark particles, and there's no Zeeman effect here. There's no, see this? This is where the white part is showering out its particles. That baby is giving off electrons. And these electrons are causing magnetic fields to vibrate, 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 and then they vibrate, and then they don't vibrate anymore because it's slowing down. That's the magnetic fields. They do the same thing as the light. Light slows down. It doesn't go the same speed. That's absolute insanity to think that. That is what Saturn looks like. And this is with a good telescope. And not only that, let me show you the article he just wrote. Before I show the article, these are all the pictures he took. These are, well, some of these are somebody else's, but he was looking at the Zeeman effect, because I think he saw these pictures that I posted years ago. And this was from Dylan Carpenter. He sent me these things, and I said, "Wow, you picked up the magnetic fields, plus you proved my dipole flood theory." These are all dipoles. Every one of these is a dipole, and it has these fields surrounding it. And the fields were very crisp. But you can see there's a ton of particles here. They're all over the place. Plus, this thing looks like a pyramid. And these look like craft going back and forth to Atlantis. I have no idea anymore. I'm telling you, my friends, there were colossal creatures living here. Where they are now, je ne sais pas. I do not know. But this really turned me on. I did a bunch of videos, no responses. However, my good friend Mason contacted me, and he said, "Can you hook me up with these guys?" And I said, I can't get back to him. Dylan sent me this. I've never heard another word from him. He's in Australia. And Rod and I work together. Rod is his uncle. And here's what we did. We did the actual photons using CMOS. CMOS is the key. That's the key. And you can pick them up. And they have like an array. It takes a ton of them at once, and then it puts them in to a raw data file that says, I am right here on this frequency here. Over here on this frequency. Down here on this frequency. Or whatever it is. And so you see them as, and he calls it stacked layering. Now don't forget, that's a red photon. Well, the green one's going to be the same if they're the same. And guess what? They are the same. That's a green photon. And they're two dipoles back to back. That's my dipole electron flood theory. I got some things I'm thinking about on that. Every day is a new day. So, but I think I got it pretty well locked down. Now, so I found these basically just after they found them at Fermilab, but they found them from smashing particles together. Huge things like this. And then you get all kinds of debris, and that's all they could see was debris. I said, I found your particles. And it did not work out well at all. You see, this is a Zeeman effect. It's identical. Now, this is with no magnetic field. Here, this is what it is. Spectral lines of mercury. Mercury is going to have a certain absorption level. Now, A is without any magnetic fields. So there's no magnetic fields, they're just pulsating outwards. Now, B is with magnetic field spectral lines split as transverse Zeeman effect. There's B. There's these sets of lines. And then C is with magnetic field split as longitudinal It's all exactly what I am showing you. And here's the Zeeman effect here in spectacular demonstration. Now, the way dipole electron flood theory works, I would have to say this is spinning this way, and this is the polar plane, even though, you know, Saturn is twisted this way. I have to think of that. Now, here's what you also have to consider. Everything we are here is going through the galaxy like on the arm of Milky Way or whatever. They're going to have some different interactions. This side is going to push harder or less than this side. You see how this one's over here and this one's bigger? I think it's maybe moving this direction. I don't know. There's a lot of thinking to do here. But this should, if you're a geek, this is like ice cream. All right, you just saw that thing right there. Now, and again, this is the same thing. Now, if you look way off to the side, you see that? That's one of its moons. And look at this. And look at the dark particles coming. There's no particle. I don't know what's going on here. I got to be honest with you. It's going to take some time. But that's absolutely the Zeeman effect. There's no question. No question whatsoever. And they know of this effect, but they don't understand. And of course, this is a planet. I'm talking about down at the electron flood theory range, where you come down here to what light really is. You see that, the black and the white? That's it right there. If you took that, that's it. That's just exactly what we were seeing. Light is two back-to-back. Planets are just one, or they're like a dipole. I can't explain all this yet, and I probably never will. How this is put together, who put it together, who's in control of the universe, how did it start, where did it come from, where it's going, where are we going? I can tell you one thing, it's nothing like you were told in school, my friends, nothing. It's so far from that, it's just beyond belief. And that's why it's so hard for people to believe it. See, there's a good-sized dipole right there. There's more dipoles. They're all dipoles everywhere. And then they can give off these fields, and they all converge on each other's fields. And anytime you see the whitish stuff, it's more luminosity. It's more photon energy. The CMOS, again, is the key to everything. And it detects energy levels. And it does it so fast and stacks them up so precisely that you can manipulate. Well, you don't manipulate it, you just look into that data. And there's so many, it's taken like, I don't know, 18 or 20 shots in a blink of an eye. And they just run right down. Just to show you, this is blue. That is fast light. That is fast light. When it comes in through the Venturi, you can't even tell it's two particles until it gets way out here. It's slowing down. There's no question it's slowing down. And there's no question we can speed it up. So how many do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. Could even be more. 27 pixels, or pictures, in this one stack. Now this was from Rod Warren. He absolutely fabulous work. And I can't get through to him either. I think I mentioned, he's Dylan's uncle. And I haven't heard from him. I hope everybody's all right. That's all I can say anymore. I don't know what to say anymore. And look at this. This is in a different way of looking at this. And that, again, my friends, is Saturn. You see that? You see all the particles surrounding it? There's the moon. These are all the fields. It's got some more moons here, I guess. As far as I can tell, these must be moons. Have to be. And you can see how the field is banging against it. And this is the Zeeman effect in spades. And this stuff here, the dark particles, I don't know. But boy, I'll tell you, look at that. Looks like a clamshell spinning in space. Yikes. Or as they would say elsewhere, ay chihuahua. I can't imagine this. It stuns me every day. And people that are interested, it's just amazing. It's fabulous. I love it. Look at that. Look at that. Yikes. Wow. I don't know what to say. I really don't know what to say anymore. Because all of this stuff is from energy related to other energy. That's all I can say. That's the best I can do. It's energy related to other energy gives you radiance. Now look at this. This is Z-killer. You look at that and you say, yikes, that's just a big blob of nonsense. And I say, yes, I agree. But when I started to really examine it, I realized, no, that's not the case. Of course you can see the dipole nature here. All right, this would be the black one, this would be the glowing one. Once again, Saturn. What's this? What's that? Look at this, like a hole coming out of it. And this is the dark particle part. You know, it's got some stripy edges around it, but that's the dark part. That's in the dipole electron flood theory, that would be the muon neutrino, that would be the electron neutrino. Now, what's all this nonsense? Because that's what I first asked him. I said, well, how can you explain all that stuff? And he says, well, I take layered pictures. And you just saw I counted like 27 layers. So he's going like, when he takes that picture. And then he cuts them to those layers. Normally they don't do that, they blend them. And that's what Dylan had, is blended layers. All right, here's Dylan's. Same stuff, but they're basically blended layers. That is not the case with Mason. And he can't get through to Dylan either, right? And I can't, so I don't know what to say. But here's, again, this is Mason. Look at this. That's our moon. What's all this stuff? What's all that stuff? And this gives off a Zeeman effect too. But that's just that's re-radiating. The other ones appear to be radiating on their own. That thing's that's not re-radiating, that's radiating. And that's Saturn. So now, let's look at this again, because it looks nonsensical when you look at it. It's just a big blob of gook. Well, let's hone in on this. Let's come out here to where we can see the Zeeman effect starting to dissipate. Right about here, he's getting layer. Every one of these is a picture. And he's just like you step down a funnel. Well, this is coming out of the funnel. And each one of those, look at that. Just look at that. Think about what you are seeing. What is this? These are actual pictures. These are not some artist's illustrations. And these are energies. That I understand. And the dark means there's very little push to shove. And the whiter it gets, there's more push to shove. That's all it is. You're pushing and shoving. The harder you hit, the more energy you get. The more energy you get, the more radiance you get. Now, Mason was able to take off all of the interference stuff that they put in cell phones and so forth to stop this kind of stuff, so that it does blend, so that you never see this. You would never, ever see this unless you did what Mason did. And I'm going to show you what he did. It's in his paper. All right, you see this? This is not understood well at all, I don't think. These are the Fraunhofer lines. And what does that mean? The sun gives off an unlimited number of radiation all up and down. However, there's dark lines. They don't emit anything in these different wavelengths. And what do the different wavelengths mean? Up here, what light spins in a circle? Up here, it's tight like this. And once it hits here, you can't see any more light at all. It's just too compact. And going the other direction, it's stretched out like this. And when it's stretched out like that, it bangs less and less hard. By the time it hits here, it just doesn't bang enough to emit any light. So this is a solar spectrum, and these are the Fraunhofer lines. Well, this guy in 1814 mapped 570 lines. Now we can detect many thousands. Why are those lines there? All right, I think I mentioned, I saw, this was an article, and they talked exactly what I'm saying. This has all the mass, this has no mass to speak of, and it has all the energy. And they said, wait, they could see, but they saw them, one over here and one over there, the black one here, the glowy one over there. They couldn't see them like we could see them in a photon, because that's all we were using was light. They started with the biggest things and they smashed into bits. I contacted Fermilab, Don Lincoln specifically, and he was rude and arrogant and dismissed me and finally blocked me. Don't ever contact us. Called me a tinfoil hat guy and an embarrassment to science. And these are the particles we found, just like they found. There's no difference. And these right here are the muon neutrinos. The black ones, they don't change. Here they are right here. And then the white ones turn into showers when they hit the Venturi. They're hitting them head on. It's the same thing as what we're doing. We're just crushing them this way. They're going sideways. They're just going that way. We're going right through, well, here it is right here. That's accelerating light. There's not a person on Earth can deny that. And here is where they explode. And this white is the recoil of the explosion. This is a subatomic nuclear explosion. And this is the kind of subatomic nuclear energy that we need. We don't need atomic energy. When they break apart, they throw off chunks like this. It will kill you. And it will degrade and still throw another one off. And then they degrade again and still throw another one off. This size will destroy the cells in your body. This is light. This is not going to destroy anything. And it doesn't destroy the CMOS either. That was the original fight I had with Fermilab and CERN and the University of Geneva. I went to the University of Geneva for particle physics, and I told them, I said, we're doing this. And they put up a big fight, same thing as Fermilab, same thing as all of them, every one of them I went to. I figured sooner or later ones, nope. Couldn't care less, not a one of them. And having the evidence, not just I think this or I think that or what do you think about this? No. Explain this to me. Blocked universally.